In the snowy landscape, the weather was clear as dark days approached, exposing cold, fuel limits, and heat loss, before stillness narrowed life inside frontier cabins. Winter pressure followed cattle routes, forcing shelter before endurance failed, as distances, weather, and fatigue narrowed options available to moving herds across open plains each season. That failure risk demanded structures slowing heat loss beyond bodies, because metabolism alone could not offset continuous exposure during winter nights on treeless ranges repeatedly encountered. Log cabins emerged because tents bled warmth through thin surfaces, allowing wind-driven convection to strip heat faster than fires replaced it during extended cold periods inland. This choice constrained mobility, but reduced convective loss under wind by replacing flexible shelter with mass-resisting pressure differentials created by steady plains winds in winter. Reduced loss shifted attention toward materials offering density and mass, because heavier substances slowed heat transfer through conduction overnight inside small enclosed volumes of cabins repeatedly. Timber availability governed design since hauled stone exceeded labor budgets, and transport distances multiplied effort beyond seasonal energy reserves available to working cowboys during winter months. Felled logs stored heat slowly, countering rapid nighttime temperature drops after fires burned down, and exterior air cooled predictably across open plains without sheltering terrain nearby. Their diameter determined insulation, demanding compromise between weight and warmth, since thicker logs retained heat better, but slowed construction speed during short autumn building windows available. Earlier material limits now shaped wall thickness and interior volume, because each added inch required more cutting, hauling, and fitting under time pressure before snowfall returned. Smaller volumes required less fuel to maintain survivable internal temperatures, as heat loss scaled with air volume and surface exposure. Inside log walls overnight repeatedly occupied. Fuel scarcity itself arose from distances separating timber and pasture, which forced daily travel that consumed time and bodily energy during already shortened winter daylight cycles. Cabins therefore clustered near trees, despite grazing advantages elsewhere available, because shelter and heat outweighed livestock efficiency during freezing months on exposed frontier ranges without protection. Proximity reduced hauling energy, preserving calories needed for winter survival when food intake fluctuated with hunting success and supply reliability across sparsely settled frontier territories overall. Those calories were finite, shaping every construction and heating decision, since exhaustion reduced labor output and increased cold injury risk during prolonged exposure periods each winter. Cabin footprints shrank as builders balanced occupancy against heat retention, because each additional body added warmth but required space and resources inside enclosed timber shells nightly. Lower ceilings followed, limiting rising warm air wasted overhead space, since heat naturally accumulated above head height when unchecked inside rectangular single-room cabins through winter nights. This vertical constraint simplified roofs while reducing exposed exterior surface, which limited conductive and radiant heat loss across winter storms, sweeping open plains and valleys repeatedly. Roof pitch still mattered, because snow loads threatened structural collapse when accumulated weight exceeded green timber strength limits during wet snowfalls common in early winter months. Steeper angles shed weight, trading headroom for continued shelter integrity, since collapse destroyed stored fuel, tools, and thermal protection at critical survival moments during storms overnight. As structure stabilized, attention turned toward sealing unavoidable air gaps, because uncontrolled airflow removed heat faster than fires could replace within enclosed log volumes at night. Chinks between logs leaked heat through convection and infiltration paths, as wind pressure forced cold air into interior spaces whenever weather shifted across open plains suddenly. Mud, clay, and moss reduced leakage by blocking airflow currents using materials that expanded when wet, tightening gaps temporarily until freezing cycles reversed those gains again. These fillers cracked when frozen, requiring maintenance despite apparent solidity, as ice expansion fractured seals and reopened leakage points during repeated freeze-thaw events throughout winter seasons. Maintenance consumed time otherwise needed for hunting or herding tasks, forcing trade-offs between food acquisition and structural heat preservation under constrained daylight hours typical of winter. Thus, cabins represented ongoing systems, not completed objects under winter, because materials, weather, and use constantly altered performance requiring observation, repair, and adaptation throughout each season. Fireplace placement followed airflow, encouraging smoke exit without heat loss by using natural draft created by vertical temperature differences inside enclosed log structures during operation daily. Central hearths radiated warmth evenly, but complicated roof penetration design since chimneys required openings that risked leaks and heat escape through roofs exposed to snow accumulation. External chimneys cooled faster, increasing draft, yet stealing internal heat as hot gases transferred energy to cold exterior masonry or timber stacks outside heated volume entirely. Draft strength balanced smoke removal against accelerated fuel consumption rates because stronger airflow increased oxygen supply and burn intensity, requiring more frequent wood loading during nights. Fuel use tied directly to wall insulation and cabin tightness as leaks, and thin walls demanded continuous heat replacement from finite wood supplies nearby each winter. Earlier, ceiling choices now dictated nightly firewood requirements inside cabins, forcing residents to predict consumption accurately to avoid cold exposure during long, unattended night intervals repeatedly. Firewood harvesting exposed hands, slowing work through numbness and injury as cold reduced dexterity and increased fracture risk while handling axes and saws outdoors daily winter. Injuries reduced labor capacity, reinforcing compact designs, requiring less fuel because diminished strength, limited hauling, cutting, and sustained effort during already exhausting winter survival cycles overall. This feedback loop favored simplicity over expansion, despite growing households, because additional rooms increased heat demand beyond fuel and labor capacity during prolonged winters on frontiers. Sleeping arrangements adapted by stacking bodies to share retained heat during nights when fire output declined and radiant warmth concentrated near occupied sleeping areas indoors together. Raised bunks avoided cold floors where dense air settled overnight as heavier cold layers pooled near ground surfaces, reducing conductive heat loss from resting bodies above. Floors themselves remained earth, acting as heat sinks during winter because soil absorbed warmth from fires and feet, lowering interior temperatures once combustion slowed overnight consistently. Some cabins added wooden planks, trading insulation for dryness inside, because raised floors reduced moisture contact with soil despite allowing more heat loss through thinner layers. Moisture management mattered because dampness accelerated conductive heat loss rates by filling air spaces within materials and transferring warmth outward faster than dry structures allowed thermally. Breathing, cooking, and snowmelt introduced water vapor continuously inside cabins, raising humidity levels that condensed on cold surfaces, increasing rot risk and undermining insulation performance time. Ventilation prevented rot, but risked flushing precious warmed air outside, forcing careful timing of door openings so oxygen entered without collapsing interior temperatures already marginal overnight. Small openings balanced oxygen needs against temperature stability inside spaces by limiting pressure-driven airflow that otherwise stripped heat rapidly from compact interiors during winter wind events. Windows remained minimal since glass was rare, and leaked heat through thin panes that transferred warmth outward faster than solid timber walls could retain overnight reliably. Oiled paper substitutes admitted light while preserving partial insulation properties by reducing direct airflow and radiant exchange compared to open apertures, despite degrading quickly under moisture. Light availability constrained daily tasks, compressing work into daylight hours, which reduced movement during coldest periods, conserving body heat and limiting unnecessary exposure to heat loss. Darkness increased stillness, reducing movement to conserve, generated warmth indoors as inactivity, lowered convective heat loss from bodies, and prevented doors opening during frigid night hours. Clothing functioned as interior insulation, complementing structural limitations during winter by trapping body-generated warmth close to skin, reducing reliance on fires when fuel ran low overnight. Cabins alone could not offset heat loss from exposed skin because conduction and evaporation continued wherever flesh met cold air, demanding behavioral adjustments beyond architecture itself. Thus, architecture integrated with behavior, timing, and bodily adaptation patterns, forming unified systems where shelter, routine, and metabolism collectively managed heat balance through winter conditions daily. By winter's depth, cabins became calibrated thermal instruments for survival. Their proportions, materials, and routines precisely tuned to environmental pressures that allowed endurance without excess energy. Soot layers slowly thickened, marginally, reducing airflow through porous interior surfaces, adding unintended insulation that slightly slowed heat loss over time as residue accumulated near ceilings. Reduced air quality was tolerated because warmth outweighed long-term respiratory consequences during winters, where immediate survival depended on temperature retention rather than distant health outcomes later. Door placement responded to wind direction to limit pressure-driven heat loss by preventing gusts from forcing cold air directly into occupied interior spaces during storms outside. Smaller doors reduced air exchange, but constrained movement and livestock access, forcing adjustments in daily routines while maintaining thermal stability, critical for human occupancy overnight periods. Some cabins added crude vestibules, creating buffer zones against cold intrusion that slowed airflow during entry, sacrificing space and materials to protect interior temperatures more consistently. These additions consumed logs, stressing already finite building material supplies and limiting ability to expand further, reinforcing restraint in cabin size and complexity over time cycles. Material scarcity forced prioritization of walls over barns or storage sheds because heated shelter directly protected human bodies, whereas animals tolerated cold with fewer structural demands. Critical supplies moved indoors to prevent freezing and spoilage losses, including food, tools, and water, crowding space but preserving functionality when external temperatures dropped below freezing. Crowding increased clutter, but reduced heat wasted on unoccupied volumes, since occupied air warmed more efficiently, improving thermal balance within limited cabin interiors during cold spells. Movement adapted to tight spaces, shaped entirely by thermal efficiency, as paths avoided cold zones and minimized door openings that disrupted stable interior temperatures at night. Daily routines synchronized with fire tending to maintain stable temperatures, requiring constant attention to fuel levels and airflow, so warmth persisted through working and resting hours. Night brought predictable heat loss, requiring preemptive fuel loading strategies before sleep, ensuring embers lasted long enough to prevent dangerous temperature drops before morning light returned. Ash-covered embers slowed combustion, stretching warmth through sleeping hours by limiting oxygen flow, reducing burn rate, and conserving fuel when supervision lapsed during extended night intervals. Corners cooled faster, creating gradients occupants learned to tolerate as heat radiated unevenly from hearths, forcing bodies toward warmer zones while accepting discomfort elsewhere inside cabins. People slept where radiant heat remained longest after fires diminished positioning, bedding near hearths and away from exterior walls that lost heat more rapidly over night hours. Experience taught heat movement better than theory or instruction. Manuals, as repeated winters revealed, airflow, conduction, and radiation patterns through direct consequence rather than abstract explanation. Failures informed future cabins, refining proportions through accumulated observation as collapsed roofs, drafty corners, and fuel shortages revealed which dimensions reliably slowed heat loss during winters. Collapsed roofs or cracked walls prompted incremental design corrections because rebuilding reused lessons learned, adjusting spans, pitches, and joints to better tolerate snow load accumulation cycles. Knowledge transferred orally, embedded in practice rather than documentation, as builders learned by watching, copying, and correcting structures that either preserved heat or failed repeatedly winter. Repeated solutions became standard because they reliably met thermal demands, reducing risk by narrowing design choices to forms proven functional across winters under frontier living conditions. Local climate differences subtly altered dimensions and construction priorities as wind exposure, snowfall type, and temperature ranges changed heat loss behavior across regional frontier landscapes seasonally. Denser woods retained heat differently, influencing regional material choices, since heavier species slowed conduction, but demanded greater labor during harvesting, hauling, cutting, fitting, assembly phases repeatedly. Logs dried and shrank, reopening gaps despite careful initial sealing, as moisture loss reduced dimensions and allowed renewed air infiltration during successive freeze-thaw cycles each winter. Builders anticipated movement, accepting maintenance as unavoidable winter labor because organic materials responded continuously to temperature and humidity changes beyond initial construction control limits imposed seasonally. Repairs aligned with weather windows when materials remained workable, since frozen mud failed as chinking. And green wood fractured easily under cold stress conditions each winter. Cabins were temporary answers to recurring, seasonal pressure, not permanence, because migration, pasture depletion, and economic shifts redirected settlement patterns across frontier regions repeatedly over time. Overbuilding made little sense given mobility and economic uncertainty, as excess labor risked loss when routes, markets, or herds shifted unexpectedly across frontier economies and seasons. Appearance mattered less than predictable thermal performance under stress, since ornament consumed time and resources without improving heat retention or structural reliability during winter exposure periods. Comfort thresholds adjusted downward as survival defined acceptable living standards, normalizing uneven warmth, restricted space, and constant maintenance demands during prolonged frontier winters without relief measures. Success meant enduring winter with minimal loss, not sustained comfort, because energy preservation outweighed convenience under persistent environmental pressure imposed by cold wind snow accumulation cycles. Heat functioned as currency exchanged between fuel, labor, and shelter, since each decision conserved or spent warmth within tightly constrained frontier energy budgets every winter season. Risk assessment relied on memory of prior winters and losses, using experience to judge tolerance limits accurately under varying weather severity and resource availability conditions seasonally. Behavior often changed first because rebuilding demanded scarce resources, so routines adapted to existing shelters before structural modification became feasible under winter labor constraints and fatigue. Extended sleep reduced activity, generated heat loss during coldest hours by limiting movement and conserving calories, otherwise expended maintaining body temperature through constant muscular activity over night periods. Meals timed before rest supported metabolic heat production overnight, as digestion generated warmth after fires declined and supplemented failing radiant output within cooling cabin interiors gradually. High-fat foods complemented cabins by sustaining internal heat generation longer when fuel supplies thinned and fires burned lower during prolonged winter scarcity periods each season repeatedly. Human bodies became active elements within the thermal system, supplying heat cabins imperfectly retained through insulation limits and leakage during extended winter nights indoors, together continually. Cabins assumed constant occupancy to remain energetically viable, relying on shared body heat to stabilize interior temperatures when fires weakened overnight and external cold intensified outside. Extreme cold sometimes exceeded design limits, forcing abandonment when fuel ran out or structures failed under sustained exposure beyond predictable seasonal variation and recovery capacity entirely. Abandoned cabins deteriorated quickly once heat and maintenance ceased, accelerating decay through moisture, intrusion, freeze-thaw cycling, insect activity, and structural fatigue over short time spans outdoors. Ruins reflected constraints more than intention or craftsmanship ambition, preserving environmental pressure as material evidence of survival limits imposed by climate, resources, and physics alone historically. Patterns in remains reveal repeated solutions to shared problems across settlements, shaped by similar climates, materials, and metabolic constraints, acting on builders and occupants alike regionally. Each structure recorded negotiation between climate, materials, and bodies, as walls, roofs, and volumes balanced heat retention, labor, fuel, and endurance under winter pressure repeatedly imposed. Winter dictated design more forcefully than culture or tradition because temperature, wind, and snow imposed non-negotiable physical limits on shelter performance and human tolerance annually recurring. Cabins stripped architecture to shelter, heat retention, and survival, eliminating features that consumed energy without improving thermal balance under sustained winter conditions on frontiers repeatedly encountered. They functioned as systems balancing inputs, losses, and human limits, where fuel, labor, body heat, and structure interacted continuously within narrow survival margins during winter months. Adaptation extended survival, but never eliminated environmental dominance, because extreme cold, wind, and scarcity ultimately exceeded human control, despite refinement, effort, and experience gained over time. Resilience appeared through repeated rebuilding under similar constraints as lessons accumulated, failures informed change, and systems stabilized without transcending physical limits imposed by winter environments persistently. Cabins anchored movement across landscapes otherwise resistant to settlement by providing temporary thermal refuge, enabling seasonal work, grazing, and travel through cold regions without permanent towns. In simplicity, cabins embodied survival shaped by unavoidable physical laws governing heat, transfer, material behavior, energy, and human endurance under frontier winter conditions repeatedly faced historically.